Okay, I will start. So we before the curfew we finish somewhere here. Okay, lecture number 3. We have to do the lecture number 3. So I will recap the some of the lectures in here. Last time we discussed the some of the part. I will just recap. So hope you remember how we can measure the strain. So we can use this kind of strain gauge to measure the strain. And so we derived some of the equations for the inclined plane stresses. And then we can find out the principal normal stresses equation and principal shear stress equation. So we derive these two equations, and then we can find out any angles, stress and nominal stress and shear stress, like this. So, and then we need to know how to draw the Morse circle. So when you draw the Morse circle, very important things are you need to find out the center. When you find out the center, you need to consider the S coordinate as a average stress, and then the Y coordinate will be 0, and then you can find out the 2 point on the circles, because given 2 stresses and shear stress are the X coordinate and Y coordinates, so you can find out that points on the circles, and you can draw the circles, and then you can find out the radius and other things, and the maximum shear stress and principal stress also you can find out from this circle, Morse circle. And there is important thing, when you select the positive shear stress in the Y directions, it should be downward. So that is a main important thing you need to keep in mind. Otherwise, when you select the rotating angle, if it is a clockwise directions, you need to draw here in the anti-clockwise direction if you select the upward. So if you select the downward, when you rotate clockwise, anti-clockwise directions, you can here also you can rotate to the anti-clockwise directions. And then so this is the when you rotate the anti-clockwise and theta angle. So the Morse circles also will be like this, and you can see new shear stresses and shear stress. And when you rotate until parallel to the x-axis, their shear stress will be absent, so no shear stress. This is the principal stresses, minimum and maximum stresses. So if you want to remove shear stress, you need to find out the principal stresses. So keep in mind, it is very important when we discuss the theory later. So you need to find out the principal stress when you eliminate the shear stress. And then we discuss these equations and find out the stresses from strain. So I'm not going to go through in detail these equations because you already did. And then some failure theories we discuss. There is basically 5 theories. So I will just briefly explain. First one is maximum principal stress theory, and second one maximum principal strain theory, and third one is maximum shear stress theory, and fourth one maximum strain energy theory, and last one is von Mises theory, that is maximum distortion strain energy theory. So those theories we can use, but when you use the one particular model, you should know what is the material, because the first one you can't use for the ductile material, but last one you can use for the ductile material. Tresca theory, that means third method, you can use for both material. That's very suitable for if you know if your material is unknown material, you can use Tresca theory to find out the failure. So you can find out that particular stress system when you're going to apply on the element. Is it safe or failure using this boundary line? We already discussed these things as well. So this one for the Rankine theory, that means first one. this one for the Tresca theory, and this is von Mises theory. So first one, third one, and fifth one. And then, yeah, this is the equation, equivalent stress. So you can use this equation if shear stress is absent. So you need to find out the sigma 1 and sigma 2 in here. And then, so this is the so you can't apply the without with the shear stress. You need to eliminate shear stress. Okay. So this is the thing. Okay. So rotating test with the standard specimen. So today we are going to discuss further more about the stress and what are the stress cycle we are going to apply on the element. So basically there is a different kind of stress range we are going to apply on the element when you design something. So you need to consider about that, but we cannot deconvolute all the stresses because this is very complex. Okay, so you can see in here, so in the first figure A, it is a aircraft when it's get off and get a landing. So what are the stresses on air, what are the stresses available on the body? So you can see that when it's get off and on air and land off, so you can see the stress vary with very complex manner. Okay. And then so you can't find out like simple sinusoidal type of stress variation in here. So you need to deconvolute this type of stresses to find out the fatigue lifetime. And this is ground vehicles, and mean kind of car or something, I see. So this is suspension load variation. You can see it's very complex, and transmission load is it is also very complex. And bracket vibration, you can see it's something like it's a continuous line, but it is a high frequency vibration or something like that. And this is bridge. So bridge also will be vibrate with the time. That's why some of the time, if it is equal that vibration resonant frequency, that bridge will be break. So this is the bridge vibration when the vehicles going through that bridge. So this kind of complex stress variation we can't handle without idea about that. So we need to. So we are going to study this kind of nature later on with the stepwise. So during this lecture, with this lecture we can't handle this kind of question, but when we are going to lecture number 6, at least you can cover this kind of nature. So yeah, so this is the other thing explaining like, so I think you already read this material as well. So I'm not going to go through these things. Yeah, I already explained this one as well. So rotating test with the standard specimen. So you can see here different type of so we need to know what are the mechanisms available to check the fatigue strength. So there is no any exact method, but there is a few methods standardized. So there's a 5 method you can see. So A, B, C, D, E. These 5 models basically scientists use for measure the fatigue strength. So first one is you can see cantilever rotating bending. So this is a specimen. And this is the load. So it's like a cantilever beam. So this is rotate with this motor, and that's why it's called cantilever rotating bending. So you can use this kind of standard specimen to check the fatigue strength. Or the mechanism B, rotating pivot bending. So you can see this is rotating. So this is test specimen. So this is rotate, and same time they apply the load at the two ends. Okay. So even though load apply in here, it will distribute to two ends. So actually we call it a fully reversed technique, fully reverse bending, because this specimen top surface, and next time it will be the bottom surface because this is rotating. So due to this loading, there is a bending moment, and this due to bending, there is a top surface will be under tension and bottom surface will be under compression. So with the rotating, each and every point, and one single time it will be in the under tension, and next second it will be under compression. So that's why it's called fully reverse bending. Okay. So later on we will discuss further more about this one. Okay, and we will name this mechanism with another scientist name as well. So rotating pure bending. And C, it is a bending cantilever eccentric crank. So you can see there's eccentric load, so not concentric load, so eccentric load. So this mechanism also we can use. And D, axial loading. This is kind of simple tensile test, but only difference is we can fluctuate our tensile load, something like under compression and tensile, something like that. And then fifth method, combined torsion and bending. So in here, when you apply the load, this specimen will be bent and at the same time torsion, like this, bend and torsion. So these are the 5 standard methods scientists will agree. So if you use fatigue strength, you can use, but if you want to introduce any other method, so you need to publish it and get that I mean kind of accreditation for that. Okay, so yeah, so I already explained that mechanism. So we will use this mechanism for the analysis. So we call this mechanism Murray test. Okay, so in the Murray test we will use this kind of specimen, but you can see until F, A, B, C, D, F, there is no any initial crack. So you can measure the total fatigue life of the specimen using this kind of specimen. But G to J, so you can see there is small cracks. So it is artificially made. Okay. So due to that, we can't find a total fatigue life. So we can find out the crack growth time period. Okay. So if you want to find out the crack growth fatigue lifetime, so you can, this is partial lifetime of the fatigue life. So if you want to find out total fatigue time, that means crack initiation and then propagation and growth and everything, account with this kind of shape of specimen. These shapes are depend on the, so if you're going to for the material fatigue test, so you basically you will use this kind of shapes. This kind of shapes they will use for the plastics, rubber kind of material. So this is kind of different kind of technique. Okay, you can see the notch in here. This is type of impact test. Okay, so hope you understand that as well. And then yeah, so I already explained crack growth data you can find out using the J to J. And in the Murray test, there is specimen dimensions are like this, because during this lecture series we are mainly focused on the metals. So this kind of shape will be used for the Murray test. So this specimen something like this. Okay, so specimen is standard size given in here. Okay, so this kind of specimen has a special features. The surface of the sample, that is specimen, should be mirror polish, and the diameter, it's 8 millimeter diameter, standard size. So and that you can see these pellets, so it's very sharply made, not sharply, smoothly. So smoothly. So this kind of specimen is very expensive. Okay, when you produce this kind of specimen, it's very expensive. So I hope you understand why they put the large fillet here, because reduce the stress conservation. Still, you don't know what is the stress concentration, but you know it's, if there is sharp edge, that sharp edge means there is a high probability to break that material at that point. That is the meaning of stress conservation. You will learn about that later. But so to reduce the stress conservation, you can put a very large fillet, then stress conservation will be distributed, so it will be delayed. So and the that specimen is not square shape, it is round shape, because if you put the square shape like this, I will draw like this. Sorry, assume this is square shape. So these sharp corners also is stress tracing point. So that's why they use round shape. So I'm talking about the side view. Okay. So this is the shape of the specimen when you look at from the side. So I heard some sound. Do you have any questions? Do you have any questions? Okay. So then this Moretes, I told you this is fully reverse technique. So you can see specimen will clamp to the machine like this. Okay. So then apply the load like this, and it will rotate with the motor, and until here to here there is no any bending movement. Shear force are not able because there is a clamp. So then so there is a bending movement, and because it is clamped, and here to here bending, that shear force will be going to be zero. You can see. Okay. So when you draw the, I hope you know how to draw the shear force diagram and bending moment diagram. So, so bending moment until this point it will be increased, and here to here it will be constant. Okay. So that's why it's called fully reverse bending. Okay. This is only pure bending, no shear, no torsion. That's why it's called fully reverse bending. Okay. So in the Murray test, we will use a fully reverse technique. Keep in mind that is very important. So this is the bending moment equation. I think you know this equation, like sigma divided by y equals m divided by I. This is the bending moment. This is second moment of inertia. This is the distance to that point, and this is stress. So when you find out stress, you can put it by this side, and this is the equation. Okay. So this is the thing what I explained. Okay. This in the Murray test, that that technique is a completely reverse bending, fully reverse bending, and 8 mm diameter solid round specimen we need to use, and polished surface free from residual stresses. Because if there any wave type of this kind of surface without like uh, polished surface, like smooth surface, this is also kind of stress conservation point. So crack will be initiated with this kind of wave. Okay, so that's why we need to eliminate this kind of surface with the polishing and put the mirror polished surface to reduce the residual stresses. So are we clear about that? So until that point, do you have any questions?
No, sir.
No. Okay. Uh, so uh, with this technique, we will draw the ascent curve. Okay. So ascent curve means actually fatigue strength, number of cycle. So uh, this test experiment parameters given in here. So you can read this one. I'm not going to go through too much about RPM value. So this RPM also you can, or you can use 3000 as well. So there is a two parameters. Okay. So you can use the motor RPM value 1500 RPM or 3000 RPM. So they use here 1500. Okay. And until break this sample, this specimen will be rotated and apply the load. So that is the mechanism. And then they will find out that our number of days. So it can be number of days, it can be hour. So they will count. So number of cycle also they can count with the sensors. So we can plot the SN curve there, because with the time strength will be reduced. So they will use the mechanism to find out the strength. So SN curve will be something like that. Okay. So N means number of cycle again. S mean we can call stress. So stress normally you will use sigma, but in the fatigue you will label as a S. Okay. So in here I need to mention one important thing. So you can't get the exact one single line with the experimental data. You will get the band, something like data point will be distributed within range. Okay, so you can select the upper boundary line and lower boundary line in this with the band. Okay, data points will be distributed like this. So per one material. Okay, so you can define different kind material has different kind of SN curve. But if you basically we will focus on the steel. So steel has a steel also has a band. Okay, it's band. So upper boundary and lower boundary. When you get the lower boundary, you can see the crack nucleation. It will take more time. So that is very significant thing in the lower boundary. The upper boundary, the crack will be nucleated very quickly, and the growing is very significant. It will take more time. So suddenly crack initiate. That means you can see. I will select one single stress. Okay. So if you apply this much of stress, assume this is a horizontal line. Okay, somewhere here. So you can see with the bottom line, low boundary, this particular material will be fair with this number of cycle, and this is with the upper boundary. But very important you need to keep in mind, if you apply the low much high stress, that crack nucleation very quickly happen. You can see in here crack nucleation very quickly with the upper boundary. With the low boundary, significant thing is not the crack nucleation, crack growing. Crack growing will be suddenly happen. Until this somewhere here, crack nucleation will be happen. Okay, so that is the important thing. You will understand what I'm explaining later. So that's about thing. So in the SN curve, number of cycle, it will be 0 to 10 to the power 6, or for an when you consider this steel, it will be 10 to the power 6 cycle. But you can't get the x-axis as an n single, I mean n value, and plot the diagram. It will be this drop happen with the number of cycle, a large number of cycles. So your plot will be something like this. You can see if you plot the SN curve like this with the linear manner. Okay, so what they did to expand this area, this is the very important area. You need to know this drop, about this drop. This is the saturation. So because this is endurance limit, so after some time it will be saturated. So that means it will not going to reduce the strength more and more, even though you apply number of cycle. Okay. So if it is break, it should be break somewhere here. After this point, it will not break, something like that. Okay. So you need to expand this area, you need to know about this data. So to expand this area, what we need to do, apply the log scale to x-axis. So if you apply the log scale, so 10 will be 1 and 100 will be 2. So this will be expand. Okay. So this is the thing. So this is a semi-log graph. So you apply the log scale to one axis to expand this curve. And then this curve is still non-linear. You can see it's not a linear curve shape. So if you want to get the linear curve, what you need to do, you need to apply the log scale to y-axis as well. So when you apply the log scale to y-axis, it will be linear like this. Okay. So then you can analyze this kind of ascent curve very easily. Another important thing, even though there is a 0 to 10 to the power, okay, this is 100. This is not much bigger thing, okay, bigger scale. I mean, this is 100 cycle, but in here you can see 10 to the power 8 number of cycle. Okay. So this is 10 to the power 7. That means 7. This is 8, 6, something like that. But you can see here very important thing. They only consider 10 to the power 3. So you need to keep it in mind. Until 10 to the power 3 cycle, there is no such significant variation of the strength. Little bit drops are there, but that drop is not significant. So you will consider initial point of this curve as a 10 to the power 3 cycle. So you need to keep in mind that. And for steel, so it will reach to endurance limit at the 10 to the power 6 cycle. Okay, somewhere here. Okay. It will reach to the endurance limit. So endurance limit means even though you apply this stress after 10 to the power 6 cycle also, that particular material will not fail because that stress not enough to break this sample. But if you apply the, so if your sample is break somewhere here, that stress not withstand this, that element will not withstand with this stress. So that is the meaning of that. So you can see here another important thing. So this is upper boundary, lower boundary also. So in here band, so we will get the average line then, and you can see the upper boundary and lower boundary as well. And yeah, I already explained that. So with the, if that particular materials after this point, the number of cycle to break it is infinite. So even though you apply an infinite number of cycles, it will not break. So yes, this one. So you can see here that the stress, even though it is reduced little bit, that number of cycle will be large. So even though within this range, stress will be reduced here to here, but number of cycle here to here. So that ratio very high. Okay. So in this region. So later on we will define the equation for this region here to here. This is end point, this is third point. Okay. So this is a normal ascent curve. So when we are going to generalize, that means when you're going to generalize, in here you have log scale, that stress unit, it can be megapascal or KSI, whatever. So when you generalize, what you need to, this is kind of, okay, it can be 1,500 or some value can be there. But when you are going to generalize, what they did, we can divide that values, all the values with constant value. That constant value will be ultimate tensile strength normally. Okay, so generalized ascent curve means that. So when you generalize that one, So y-axis also will be within some 0 to 1 value. Not that much of large values will be there. So you can see generalizing curve. So that stress will be divided by ultimate tensile strength of that particular material. So if it is aluminium, it should be aluminium ultimate tensile strength of aluminium. So normalizing means that normalizing, generalize or normalize. So normalizing means, so you need to divide that stresses. You can see, as I told you, 0 to in here you don't want to go to 0 because no data points available at the 0. So they draw here 0.4 to 1. You can see here upper boundary and lower boundary. Okay, but very important thing, significant thing you can see here. So the lower boundary will reach to endurance limit very quickly rather than upper boundary. So in here, lower boundary is reached to 10 to the power 6 cycle, and this one is 4 times 10 to the power 6 cycle. So lower boundary will, if it is reached to very quickly, so like this. So even though average line also will be reached to after this point. So this is very quickly reached. So you need to consider the lower boundary there to analyze. Okay? So you can see for the analysis you need to use the lower boundary, not the upper boundary of average line, because it will reach to very quickly to the endurance limit. So as I told you, initial point normally we will consider 10 to the power 3 cycle, and for steel the endurance limit reach 10 to the power 6 cycle. Okay, this is endurance limit. So strength will not going much lower rather than after this point, this stress. Okay, this is half of the ultimate tensile strength. That's the meaning of here 0.5. So if you want to find out 10 to the power 3 6 cycles strength, so what you need to do, if you know the SU value, ultimate tensile strength, you need to multiply 0.5. From 0.5, if you multiply that value, you will get the endurance limit. And 10 to the power 3 cycle, it will reduce 10%. So you can find out it that ultimate tensile strength by multiplying 0.9. So normally in the questions they will provide for us BHU9, that means hardness. From the hardness, you should have the ability to find out the ultimate tensile strength. So there is a relation between those properties. So there is a relationship between, so they will provide. So in here also same. So if you don't know SU value, if they provide hardness, you need to find the ultimate tensile strength first, then find out the endurance limit. So as I told you, this is the first point, and this is second point. That means end point of this linear region. That is the 10 to the power 6 cycle. That is the endurance limit again. So that nomenclature will be provided the endurance limit is Sn prime. Okay, Sn dash O is Sn prime. So it is approximately 0.5 times SU. Okay. So this is the relationship between the tensile strength and alternating fatigue strength. So you can see the variations. So we will consider this region, fatigue ratio 0.5. Tensile test mean strength mean this endurance limit will be provided. Sorry, this ultimate tensile strength represent the tensile strength. So it will provide from tensile strength. Okay, so you can see if that ratio 0.6, this is the curve. But most of the data, this is real experimental data. So most of the data distribute around this axis, this line. Okay, you can see. So these are the relations between these two properties. Okay. And then you can read and understand this slide. And this is the when that specimen preparations. That means if that specimen, if it is for example, that is a rough surface, or that kind of nature, according to that nature, this way, fatigue limit, and that means endurance limit, and ultimate tensile resistance value relationship, it will be changed. You can see severely notched specimen. This is the data band. So real experimental data band is like this. And if it is a corroded specimen, it will be something like that. And if it is normal polished specimen, this is the range band, you can see. So in here also you can see that. Okay. And this is for the rare cases, that is ideal specimen. Okay. This region. So this is the summary. So you can get the SN curve like this. Then initial point and 3 and 6 is the end point of this linear region. Then induced limit range. So this is the generalized SN curve again. So then we can derive the equation for this region, as I told you earlier. So if you know the equation, you can find out at any point on this curve the stress and number of circles for that stress, isn't it? So this is the equation. If it is stress or strength equal A times n to the power B, A and B are constant. Okay. So you can derive that equation, you can rearrange that equation with the log. You can introduce log here, then it will expand like this: log S equal log A plus B log N. So you can use this, either this equation or this equation. So if you know 10 to the power 3 cycle strength value, you know number of cycles is 10 to the power 3. It is obvious, no? Because 10 to the power 3 cycles strength means that number of cycles 10 to the power 3. So you know these two values, and if you know 10 to the power 6 cycle is strength, and that is number of cycles 10 to the power 6. So is strength, if you know these two values. So two unknown, two equation we have, you can find out the A and B values. Then you know this equation very good, because A and B is defined. The different equations, different A, B values. You need to find out that A, B value. So as I told you earlier, when you are going to find out this endurance limit value, that means SN prime value is equal to 0.5 SU. So sometime in the questions, the SU will not provide directly. They will provide the hardness. So you should know the relation between the hardness and strength. So
Sir, I have a question.
yeah, you can ask.
Can you go to the previous?
Yeah.
So in the slide, the SN values at S 10 to the minus 6, 10 to the 6, right? So after 10 to the 6 cycles, it won't fail, right?
Yeah, it won't fail.
So, but that's at approximately, we'll say 0.33 stresses. So what if we increase the stress? Will it then fail?
So no. So during this curve, we are not going to change the stress pattern. So we will apply the same stress. So if during this number of cycle, that stress pattern will not change. So if you are going to increase the stress again, so this curve is not valid anymore.
So this curve is for one stress applied
One stress curve.
If we
something like, okay, I will draw
so
this. Okay, let me explain. So if we apply this kind of stress, alternating stress, okay, so this is stress, this is time, the time. So you are not going to change this amplitude or frequency. So you will apply same cycle during the time. Did you get what I'm explaining?
Okay, if we're not, yeah, I understand that same stress, but if we're not changing the stress, why is the y value, why is it decreasing?
Because in here, if you remember the earlier slide, they explain the some kind of crack nucleations. So with the number of cycle inside the material, crack will be initiated because the material is not perfect. Crystalline structure is not perfect. So that defects are moving around and around inside the material and form the crack, and it will be nucleated growth. So that's why it's increase the reduce the strength. Did you get what I'm explaining?
Right, okay, sorry. Yeah, I get that.
Because so if you can't understand it very simply, I can say when you break the copper wire, what you're going to do normally. If you want to break the copper wire,
Bend it?
yeah, you will apply that bending cycle few number of cycles, no? Isn't it?
Yes, sir.
So, but you are not going to change the US force. You will apply same force and bend it, and I mean tension. You will bend upward and downward with the same stress. I mean same load. You
Yeah.
are going to apply the hard. I mean you are not going to bend it very hard manner. Softly you will bend it few more cycles. Okay, when you bend it 20 cycle low, 15 cycle, it will break, isn't it?
Yeah.
So that is a nature. So that is a fatigue nature.
Yeah.
So
Okay, I understand.
same thing here. So, that question is very important. So this is belong to one single stress cycle. That means one single pattern of stress cycle. So you will learn about if you apply few type of stress cycle. Okay, assume like this. If you are going to apply this type of stress in the same element, and this time this much of amplitude. So this kind of nature you will learn later, but for that you need to know what, to analyze the one single stress cycle. Okay, so in here we are only deal with the one single cycle. Later on we will introduce the more and more cycles, I mean more and more stress pattern in the one component. Is it clear here? Yeah.
Yes, sir. Yes, sir. I understand.
Okay. Can I move?
Yeah.
Okay. So this is a brittle hardness and endurance, ultimate tensile strength relationship. And they explain what is the brittle hardness. So you know there is a indenter. So with the force, that indenter will be connected to the material. That force will be constant. Okay, so that force should be constant value. So known value, and with that there is a actually tables for that. Okay, you can select the load value 10 kilonewton or 5 kilonewton, 20 kilonewton. So that 10, if you select the 10 kilonewton, you have the tables, and after apply this load on this indenter, so it will penetrate to the material. This is the material, so that surface will be make the impression. Okay, so that impression has a dimensions. With the dimension, so if it is soft material, what happens? That indenter will be penetrated to the inside more and more. If it is too hard, it will not penetrate to the inside too much. So with that impressions dimension, we can get the idea about the hardness respect to this material. So that tables given that values, with this dimension, if you penetrate this much inside, whatever, this dimension will be changed. Di will equal to D. Okay, so that's mean this particular material and this particular material hardness is equal. So like that, if it is not penetrates that much, that means this one more harder than this one. If it is penetrate to this much inside the material, that means it's soft, very soft. So there is a scale and other things, so you can read the Brinell hardness value. So if you have Brinell hardness, so this is the equation for that, the relationship between the force, and so that the table developed with this equation. Okay, I'm not going to go through the Brinell hardness theory. So if you want, if you're more interested about the Brinell hardness test, so you can read them, read in the internet, and if you have any question about that, you can ask. So then this is the relationship between the Brinell hardness and ultimate tensile strength. But this is valid for the hardness if it is less than 350. So you can't apply this equation, the Brinell hardness, if it is higher than 350 material. So material hardness is 360, you can't apply this equation. Okay, so please check in your questions in the exam, even though exam or anywhere. So that hardness, if it is higher than 350, you can't apply this equation. Please check it. So if it is less than 350, this equation valid. So this approximate equal 3.45 times BHN value. Okay, so what you need to do, if you have BHN value, assume it is 200, so 3.45 times 200, so you will get the ultimate tensile strength value in megapascal. Okay, so that's how you need to use this equation. So that is a relationship between the ultimate tensile strength and Brinell hardness. Okay. So this is the again explained with the graph. Okay, so you can see the different materials has a different relationship. That relationship for the steel. Okay, so if you use in the question is the aluminium, they will provide the relationship. Okay, this is very for steel. So you can see the steel that tensile strength and hardness, BHN hardness relationship in here. Okay, so you can see here, and this is a malleable cast iron, this region, and this is gray cast iron. So likewise, and so they will provide another relationship. So if you want to find out the 10 to the power 3 cycle strength of the material, the fatigue strength of material, it also providing here 3.10 BHN times BHN. So if you have BHN value, assume same value 200, so you need to multiply by 3.1, then you will get the 10 to the power 3 cycle strength. Okay, this is relationship between BHN and other strength, ultimate tensile strength to fatigue 10 to the power 3 cycle is strength to 10 to the power 6 cycle. This is endurance limit. So endurance limit Sn prime, it is equal 1.72 BH. So likewise, you can use these two equations. They will provide this equation. Okay, you don't want to keep in mind this equation, but this equation, if you can just keep it in mind. Okay, sometimes they will not provide this equation. If they provide this, it's okay, but this is the thing. Most of the time they will use in the question. So normally these two not usually use, but they, if you want to use, they will provide it. So so there is another cast ferrous metal, that means cast iron or cast steel. So the endurance limit at 10 to the power 6 cycle, it is 0.4, even though it is still 0.5 times SU. So the cast iron, it is 0.4 SU. So I told you the endurance limit will be changed with the material to material. So we are basically focusing here steel. Sometimes it will we will use some equation for the aluminium, but not for other metals. Okay, so basically we will use steel. Okay, so there is one questions. Okay, example. So how to use that equation? So if you have BHN value in here, Rockwell value. Rockwell also one kind of hardness measurement. Okay, there is a three method to measure the hardness: Vickers hardness, Rockwell hardness, and Brinell hardness. So they provide the Brinell hardness and Rockwell hardness relationship. So what you need to do, if you have Rockwell hardness, you need to convert that Rockwell hardness value to Brinell hardness value, then find out the strength. So 10 to the power 3 cycle strength, this is the value, because this equation, this one. Okay, so if you know the BHN value, you can multiply by 3.1 and get 10 to the power 3 cycle strength, 10 to the power 6 cycle, 1.72 times BHN value. So this is value, and endurance, ultimate tensile strength is 3.45 times BHN value. So this is just to show how to use that equation. And this is SN curve, that number of cycles, and then what 3, 7, 6, this is the steel. So just in here, fatigue lifetime will vary with the load type. So there is a basically there is a 3 load type: axial load, and bending load, and torsion load. So with this basic loading time, that fatigue lifetime will be changed, and specimen size and surface finish. So those are the 3 parameters fatigue the fatigue life depend. So if you change the specimen size, that's why in the Murray test, if you remember, when I explained, I told you that dimension should be 8 millimeter. So if you change that size without fixing that dimension, that fatigue life will be changed. Then you can't compare the material's strength, because sometimes strength vary because of that fatigue life will vary due to specimen size, not because of the material. So that's why we need to fix that parameter. So surface finish, that's why we push the mirror polish. If you get the different surface mirror without mirror polish, like hot roll sample or cast sample, aniline sample, like this different kind of samples, if you got surface finish different, so we can't get the comparison again. So that's why we need to keep the one single method to finish the surface. Otherwise, the fatigue lifetime will be vary with the surface finish. So that's mean these are some of the parameters govern the fatigue life. Okay. Even though so you can see 8 millimeter diameter, and so you can introduce now in here. So when that equation, if you remember, 10 to the power 6 cycle strength equals 0.5 SU. So you can introduce still we are strict with this assumption. Okay, there is no any stress conservation point. That means there is no any hole or defects. We assume like this: there is no any defects, no crack, no holes, no pilot, like that, no groove, no any kind of stress considerations are not available in the sample. We assume sample free from the stress consideration, and complete reverse bending. Still we are stick with the complete reverse loading. So we will later on we will learn other type of loading as well, but complete reverse bending, that means if we apply plus 50 tension, same time you will apply the minus 50 compression as well. So that cycle vary plus 50 to 50 to minus 50. Or if it is 100 plus 100, it will move to the minus 100 as well. That's the meaning of complete reverse. And so still we are strict with this assumption: homogeneous material without residual stress. So material should be homogeneous. without residual stresses. And mainly, as I told you, mainly we are considering that material is steel. So this this slide, during this slide, basically they explain that weakest point, it is available the loading point. Okay, so when you apply the load, that loading point is the weakest point, because that is the higher bending moment point. Okay, so there is a maximum stress available point. So still we don't have any stress conservation point. So in the specimen, when you consider this shape of, okay, this is specimen, assume this is supported this 2n. So if you apply load like this, so this is the point maximum stress available. Okay, so this is the weakest point there. Okay, so you can apply axial load. There is a different kind of load type. Axial load, as I told you, axial load and bending load. So axial load and bending load, so you can use same theory. It's not too much different. Okay. So say same theory you can use, no worries. So 0.9 SU, 10 to the power 3 cycle. And torsional load, it will be different. So you need to consider different aspect. Okay, but in here, what I need to explain, so if you remember distortion energy theory, so we need to eliminate the torsional load, I mean shear stresses. Okay. And we will produce that principal stress loads pattern. So this theory we will use later on to calculate this kind of thing. Okay, and yeah, you can see in here. So if you use this equation, this is the, I will use that mean DE theory, distortion energy theory. So this is the equivalent stress. This is the principal two stresses. So these small circles row around the center. Okay, that means this is fully reversed. Fully reversed. You can see sigma 1 and sigma 2, it is equal, fully reversed, and the shear stress also equal to this value. The origin is the center. So then sigma 1 and sigma 2 is equal to torsion. So then you can substitute here. So then equivalent stress is equal to root 3 times torsional shear stress. So this is the value. So when you get the root 3 values, 1 upon root 3. So this is the value. So this is the relationship. Okay. So we need to multiply 0.58. That is the load factor. Okay. So normally we will introduce these parameters, what I explained in here: load, specimen, and surface, with influence. I mean, it can be influenced in a negative manner or positive manner. So if it is influence, normally it will influence in the negative manner. So it will reduce the strength. So load, with the load, strength will reduce. So you need to multiply by some factor. This also influence the strength. So you need to multiply another factor. So this factor, load factor. Specimen size we will call the dimension factor or size factor. This is a surface factor. So we will call this one CL. This is CD. This is CS. So in here, load factor for the torsional load CL equal to 0.58. You need to multiply that endurance limit value from 0.58 to get the actual endurance limit. Yes. So this is the summary. So if you have to apply reverse or rotating bending, CL value equals 1. So you don't want to multiply, even though you multiply this one, it's not changed. But axial load 0.9. axial load with the bending. So this is the shear within the 0.6 and 0.85. Torsional 0.5 for the ductile. Normally we are not focusing the brittle material too much, but it is a brittle, it is 0.8. You need to multiply this value. 10 to the power 3 it is not affect, but 10 to the power 6 it will affect. Okay? 10 to the power 3 you will not want to multiply this one. Okay, I'm sorry. 10 to the power 3 it will not affect by these factors because it is very beginning of these cycles. So 10 to the power 6 means it is propagate too much time. So load and surface factor is significantly affected to 10 to the power 6 cycle. 10 to the power 3 cycle, I couldn't tell you. 10 to the power 3 cycle not change with these factors. So you can see here some of the steel. This is ultimate shear strength. Okay, ultimate shear strength. This is ultimate strength and ultimate shear strength relationship for this steel. Because when you are going to torsional load, we don't have the ultimate tensile strength. We should consider the ultimate shear stress. Okay. So if they provide this relationship, if you know this value, you can find out the ultimate shear strength. That S subscription US means ultimate shear strength. So this is for cast iron, this is non-ferrous. So normally we are not focusing these two too much, but still we use focus. Hello.
Excuse me, sir.
Yes. Yes.
Sir, can you differentiate between what is SU and SUS, the ultimate tensile strength and shear strength? Like, give a briefing about what it is.
Because if there is only axial load or bending, because it is a kind of tensile load. Okay, so it is not the shear force. Okay, I will draw here. So okay, so this is kind of tensile load, isn't it? So if you apply in here this kind of, this will bend. So this is bending load. So even though this is bending or axial load, so this is also this axis. When you consider this axis, this is axial load. But these two load we can analyze with the tensile graph. This kind of graph, isn't it? But if you element in under shear force it is applied on the surface like this. So we can't analyze this kind of nature with this kind of graph. So you need to this is the tensile load or bending load. Okay, I will put T. This is stress. Okay, this is time. Okay, time with the time you need to consider this is shear stress. Okay, with this one, this shape will be changed. If you remember, I told you, shape not remaining as a same shape will be destroyed. So the shear force has a different ultimate strength. So this ultimate strength and this ultimate strength different. This is called SU. This is called SUS. This is ultimate shear strength. This is ultimate tensile strength. Is it clear?
Yes, sir. Yes. Thank you, sir.
So I will move surface finish. So as I told you, surface finish actually depend on the manufacturing process. So they will normally provide the this manufacturing process in the questions, like is it machine sample or machine sample will they mean that finished by machining, or is it hot roll sample or cold roll sample, like that they will provide. So according to that you need to find out the surface factor. For that they will provide the graph. So this is the graph. There is a curve you can see. So this is mirror polish sample. If you have mirror polish sample, you can see surface factor. This y-axis surface factor. This is tensile strength. So keep it mind. each and everything you need to know the ultimate, at least should know the ultimate tensile strength. So normally you will find out the ultimate tensile strength at the very beginning. So if you know the ultimate tensile strength, so if you know what is the type of surface finish, you can find out the surface factor, because assume ultimate tensile strength 1000, you can draw the line. So if it is mirror sample, it is 1, it will not change. But it's fine ground or commercial polish, so you can see if it is 1000, again 0.9 that one surface factor. But if it's machine sample at 1000, it is 0.7. If it is hot roll sample, it is in between 0.4 and 0.5. So when you get this kind of value, get this reasonable value, okay? Don't get 0.48 or 49, because it is exactly the middle point. Okay, so you can get the 0.45 or 46. Don't get 49 or something like that. And Ashford sample, it is different value like that. So they will provide the surface finish type. So you need to select the surface factor according to that. So I hope you understand that. Okay. So then, sorry. Okay. Yeah. So this is the again relationship between the introduced limit and surface finish. So again, this is not affect to the 10 to the power 3 cycle. It will only affect to the endurance limit. Okay. So keep in mind, load factor or surface factor or size factor, it will not affect to the 10 to the power 3 cycle. That is the initial point of this curve, SN curve. It is affect to the endurance limit point. So size factor, so size, when we change the size, you can see here relationship. So specimen with the specimen diameter, this that size factor will be changed. So the specimen diameter in here it is in inch. Okay, so don't think say 0.8 is a millimeter or something like that. So inch. So you can convert to this inch value to millimeter. So you can see 0.4 inch. Until that point, that size factor equal to 1. Okay, that dimensions, if it is more than 0.4 inch, that size factor will reduce to 0.9, and it will go until to 2 inch. But if it is more than 2 inch, 2 inch means it is around, you need to multiply by 21 millimeter. I don't remember what is the conversion of the millimeter and relation between the inch and millimeter. You can convert it and check it. So after that millimeter value, to relevant to this inch value, so it will drop more and more. Okay, so we are not dealing above 2 inch diameter cases. Okay, in here, so we are dealing with the lower than 2 inch questions. In the question, they will not provide the lower value more than 2 inch. So less than 2 inch, sorry. So that is the size factor effect. So it is also not affect to 10 to the power 6 cycle. It will affect to the 10 to the power 6 cycle again. So the load type, with the load type, the size, if it is 10 lower than 10 millimeter, so size factor it is 1, and if it is in between 10 and 50 millimeter, it is 0.9. Yeah, I think 0.4, if it is converted to the millimeter, it will be 10, something like that. And if it is higher than 10, and this is I think 50, so that's why it's mentioned here. So bending and torsion, you can select. So in the particular questions, you need to find out what is the loading type. If it is a bending, check the dimension. So if it is less than 10 millimeter, CD load factor is 1. Likewise, if it's axial load type, you don't want to consider about the dimension, because axial load, it will along the axis, so you don't want to worry about the dimensions. So this, it is apply on the axis, center axis. So CD is always 1. So it is also not affected to 10 to the power 6 cycle. Yes. So this is the final equation now. So if that, as I told you, 10 to the power 6 cycle, these factors not affect, but 10 to the power 6 cycle, it will affect. So endurance limit, if it is equal to 0.5 SU, if it is ideal specimen, but this is non-ideal specimen, because if it is not mirror polish, it is addressed in here. If it is a different size, it is addressed in here. And if it is different loading type, without complete fully reverse bending, it is addressed in here. So different load type, different size, different surface. So this is the final equation for the 10 to the power 6 cycle strength. So you can see, so definitely it is less than 0.5 SU, because Sn prime means 0.5 SU. So when you substitute here 0.5 SU, so those value not higher than 1. Always it is lower than 1. So this value will be lower than earlier ideal specimen strength. So any question until this point? So basically you need to find out what is the type of load and find out the load value, load factor and size factor according to dimension. Surface factor you need to find out the graph, the figure. At the 10 to the power 3 cycle, for the bending load, same equation. Even though it's size change or load type change, surface change, it's not affect. And torsional load, so you can't find out the 10 to the power 3 cycle strength with the SU. It is ultimate shear strength. Okay, so it is equal 0.8 SU. I explained here for steel. For a steel, relationship between the ultimate tensile strength and ultimate shear strength. This is the relationship. So you can substitute here. This is the value for the network. Okay, and axial load, it is 0.75 SU. Okay, so at the 10 to the power 3 cycle. So it's not changed with the size and load and surface. So I hope understand that part as well. So this is ideal specimen. This is the summary actually. So it's a fully reverse bending. So 0.9 SU at 10 to the power 3 cycle and 0.5 SU at the 10 to the power 6 cycle. This is ideal specimen SN curve. And if it is non-ideal specimen without stress tracer, so still we are not discussed this stress tracer. We assume there is no any stresses, because if you remember, I explained there is a 4 assumption at the very beginning when we explain this one. So 10 to the power 3 cycle point is not changed, even though we apply the different type of load like that. So, but 10 to the power 6 cycle, it's dropped. Strength will be dropped. So endurance limit will be dropped. You can see. So this is ideal specimen SN curve. This is non-ideal specimen without stress tracer. So in this example, so you can read this example. A steel tension bar spring has a solid round 19 millimeter diameter section blends smoothly at each end with the largest thin sections. It is subject to a completely reverse nominal torsional stress of 210 megapascal. Stress constraint is negligible and the surface are machined. Estimate the fatigue life for the case of BHN equals 240. So you need to estimate the fatigue life. So any questions?
So
Yeah.
So in the previous slide,
Yeah. Okay. Here.
so CS, CL, CD into
Yeah.
0. Is it equal to shear force? S means shear force or?
You mean this is
No. The whole thing. The
this one?
equation.
This equation?
Yeah.
No. This is not a shear force. This is actually 10 to the power 6 cycle fatigue strength. So
Strength.
strength, fatigue strength. This y-axis is a fatigue strength. This is normalized strength because we divide by SU. I discussed that one. So this is stress actually. Okay, fatigue
Okay.
strength, because fatigue strength will reduce with the number of cycle. Okay, if it is can survive with that stress until 10 to the power 6 cycle, it will survive until infinite fatigue lifetime. But if it is fail somewhere here, I mean, if it is break somewhere here, so it will not reach to endurance limit. That's the meaning of that.
Okay, sir.
So this is not the shear stress. Okay, shear stress included in here. If it is torsional load, sorry, here we will address that in here with the load factor. So in that slide we explain here. Yeah, in here with the load factor we will address the torsional load. With the torsional load, normally shear force will be account. Is it
Okay,
clear?
sir.
Okay.
Okay. Thank you.
So with these questions, we need to find out the fatigue life. Okay, estimate the fatigue life. That means number of cycles. Okay, to fail. So you have BHN value they provide in here. So you know the relationship. So you can find out the ultimate tensile strength. You can see they always find out the ultimate tensile strength at the very beginning. Okay, and CL, because this is torsional stress. So the torsional stress, you can see the load factor 0.58, and dimension they provide in here 19 millimeter diameter. So it is higher than 10 millimeter. If it is torsional load, CD is 0.9. Okay, and CS surface factor. So for that, ultimate stress already you know. So you can draw the line around 828, and that sample, is it machine diameter? So they didn't mention about the surface of machine. Yeah, in it they mention. So machine sample. So you need to select this curve and draw the line and find out the value. So they consider 0.73. You can see over here. Okay. So then this is this. Okay. Sorry, in here it should be SN. Okay, not SU. This should be SN prime. Okay, SN prime equals 0.5 SU. Okay, this way. So this is ideal case. That means the sample should be 8 millimeter diameter and mirror polish, fully reverse stress apply on that specimen. So this is ideal specimen. That three conditions should be satisfied to the ideal specimen. So this is the endurance limit if it is ideal specimen. Okay. So these are the steps how to do that. Okay. So at the 10 to the power 6 cycle, actual strain, because of that load factor and size factor and surface factor, so you need to use this equation. So this is actual strength. So there is a strength reduction because of these factors. So you need to multiply this SN prime by that factors. So you already know that values. So you can substitute here and find out the 10 to the power 6 cycle strength. So you can see here, even though it is 414, in here it is 158. Okay, so this is normalizing. Okay, don't worry about that. When you draw the graph, you need to divide by SU. That is normalizing, generalizing. So we will draw the y-axis between 0 and 1. That's why. So at the 10 to the power 3 cycle, that tensile, fatigue strength, it is equal 0.9. This is this in this equation it is torsional load. That's why they consider ultimate shear strength. Okay. So ultimate shear strength. So you can multiply that by that values and find out the 10 to the power 3 cycle strength, and this is normalizing. You can see that value 0.703. So you can draw the curve like this, SN curve. So if you have graph sheet, you can, so if they provide graph sheet, you need to draw the this curve with this scale. But even though they didn't provide the graph sheet, at least draw the reasonable curve. I mean, if it is 596 and 158 cannot be somewhere here, okay? It cannot be like this. Something reasonable variation should be there, okay? Okay. So this is the ideal fully reverse bending system. So if you can see this question, we already know that ideal specimen endurance limit. Here it's around 440, something like that. So we can find out so we already know this data point now. Okay, these values we know. We know x coordinate and y coordinate in here. In here, x coordinate 10 to the power 6, y coordinate 158 megapascal. In here is 10 to the power 3, y coordinate 596 megapascal. So you can use that equation. We know the equation. S equals a times n to the power b. So you can expand or rearrange that equation with the log. So you can substitute to 10 to the power 3 cycle data in here, 10 to the power 6 cycle data in here, like that. So in here you can see, you can find out a and b with solving equation 1 and 2. So a and b will be something like that. So this is the equation. This is the equation for that SN curve. Okay. So what you can do now, if you know the stress. So in the question, I will go to the question again. In the question in here, the stress is 210 megapascal. So if you know the equation of this curve, so if you know the stress value, you can find out the fatigue life. So you are going to find out these 2 points to derive that equation. Derive means you are going to define that equation. So after define that equation, you can substitute the x coordinate or y coordinate and find out the x coordinate. So that's the thing. So you know stress now. This 210, substitute here and find out the number of cycles. So do you have any questions about that example? If you have any question, you can ask. Otherwise, I will move. Okay. So are you there?
Yes.
Yes, sir.
Okay.
Sir.
I can't give the breaks now, so can I move?
Yes, sir.
So, yeah.
Yes, sir.
Okay. In here, this is a we discussed until this point for the steel. So if we have non-ferrous material, that means aluminium or copper, different kind of other element without ferrous material, non-ferrous alloys. So you need to consider the endurance limit for the soft alloys. It is around 5 times 10 to the power 8 cycle. So it is not a 10 to the power 6. Okay. So you need to keep it in mind. 10 to the power 6 for only valid for the steel, not for every material, each and every material. But basically in this chapter and this session, we will just only focus on the steel. So that's why we are dealing with the 10 to the power 6 always. But in this slide, they want to mention there's another endurance limit for the different kind of materials. Okay. So you can see here. So I'm not going to go through that one too much. So the harder material, it has a different values like that. So yeah, again, this is a aluminium alloys. You can see SN curve, and this is a different alloy material has a different endurance limit and difference fatigue lifetime. So this is at the endurance limit. This is the number of cycle. Like in the steel 10 to the power 6 cycle, Sn dash in here, it is 5 times 10 to the power 8. Nickel, titanium, copper, magnesium, yeah, likewise. So that's all about the lecture. So do you have any questions about the lecture?
No, sir.
Okay, so can I move the tutorial? Okay, if you have any questions about lecture, just raise that one. Otherwise, I will move to the tutorial. So hope you don't have any question about the lecture. So tutorial 2. So I didn't do that one, no?
No, sir.
Okay. So did you do that one with, I mean, as exercise at the home? Because you have 3 weeks, I think. Did you try? So you have solution, you have questions as well. Did you try? Without doing that questions, because tutorial number 2, 3, 4, I think it's not too difficult. But after, so at the exam, you will get the question like tutorial number 6 or something like that. Okay. So you will not do this kind of questions. You will not get. So this is a basic steps. So tutorial number 3, you can see same questions, they will develop. Okay. If you look at that tutorial, you can see. So in the, I will read these questions first, and I will explain. If you have any questions, raise your hand, means you can ask. Okay. So the shaft shown in figure 2, so you can see there is no any pillar to something, okay? No stress racer. Shown figure, machine from alloy steel, heat treated to 320 BHN. So they provide BHN value, that means hardness, and rotate at high speed while the imposed load F remains static. So F is remaining static. First thing, you need to draw the shear force and bending moment diagram. So in this tutorial only you have draw the shear. This not you have. They will ask for the shear force diagram and bending moment diagram. Later on, they will not ask for the bending moment diagram and shear force diagram, because you should know. You need to draw it and find out the answers for that. Okay. So don't think you need. If they ask, only you need to draw it. Sometimes you need to. It's according to question. It will be depend, but you need to. If they didn't ask, you should know where you need to draw the shear force diagram and bending moment diagram. So in this question, they asked that. Okay. So what is the maximum allowable load so that the shaft will have infinite fatigue life? That means 10 to the power 6 cycle maximum load you need to find it, because this is steel. And then what is the maximum allowable load so that shaft will have 5 times 10 to the power 4 cycle fatigue life? That means it has different values. So there is answers already, but I will explain. So dimensions provide. So you can see the force apply. It is not the mid span, so it is little bit deviate from the mid point. Yeah, L2 is 150. It is 100. So dimensions are given. The diameter is 30 millimeter, and they normally provide this table. Okay. And they will normally provide this graph as well to find out the CL and CD and CS. So very first thing, you need to find out the CS, CD, CL and ultimate stress strength. You can see in these questions. Okay, for that they ask the shear force and bending moment diagram. So you need to draw like this. So shear force diagram. Okay, can you answer me? Did you know how to draw? Did you know how to draw the shear force diagram and bending moment diagram? Do you have some particular course to do that?
Yes, sir. We did that last year.
Okay, now I can't take you to the board and ask how to draw and something like that, but I hope you can do that. Okay, so if you have any difficulty to draw the shear force diagram and bending moment diagram, so please do the exercise on it. Okay, that is very important, because in these lessons we are not going, I mean this subject, this module, we are not going to focus on the shear force diagram and bending moment diagram ability, but you should know that. Okay? So we are not going to teach you that. So if you have any question how to draw that one, I can guide you, but I cannot explain now because it will take more time. Okay, so there is 3 methods to draw the bending moment diagram and shear force diagram. So at least you should know 1 method. Okay. So do you have any question about this shear force diagram, how to draw that and something? So in here normally you need to find the reactions. So if it is equilibrium system, the force should be equilibrium, it should be equal to 0 force balance. So these 2 reactions and this horizontal force, sorry, vertical force, it should be equal to 0, summation of these forces. And bending moment also should be around some point, it should be equal to 0. So using that 2 theory, you need to find out these 2 forces. Okay, so F equal, if you put the FA and FB, this is point B and point A, FA plus FB equal F. So there is a 2 unknowns, so you can get the bending moment equation to get the other equation. Then solve that equation, you will get the 2 ends reactions values with F. And then A to B shear force variation in profile is here. So shear force profile. So at the A, shear force will upward, and until this point shear force will not change, and after F force apply it will be going to downwards and minus this value magnitude, and at this point it will become to 0. Okay, so simply I can say like that. And the bending moment at this point should be 0, and this end also should be 0. That the loading point will be maximum. So you can get the bending moment at this point from this way and this way. You can select which point you need to get. So in these equations, this one they will get from this side, this one they will get from this side. So this is the bending moment. Those 2 values should be equal. So this is the maximum bending moment point. You can see loading point. Still you have the 1 weaker point, the loading point only. So then CL, CD. So I think you know how to get that value now. CL, because this is a bending question. Bending. So CL value will be 1. CD, if you remember, diameter is 30 millimeter. So it is in between these two. So CD value will be 0.9. The CS, you need to use that graph. For that, you need to know the ultimate tensile strength, because S axis is ultimate tensile strength. So use that equation, but BHN value, it is 320. So it is less than 350. That's why you can use this equation. So ultimate strength you can find and draw the line.
Excuse me, sir.
Yeah, you can ask.
Could you please share the screen for us?
Oh, sorry, I didn't share that.
No.
Oh, why don't? Okay, I forgot that. So no one told me. I don't know. I didn't share because I switched to that slide and couldn't remember. Okay. Sorry. So when I explain how you get my explanation, I don't know. I thought you can see my.
It's referred to the document.
Okay, I'm sorry for that.
No.
Okay. So
It's
at
okay.
least you guys should be telling me. Okay. I'm sorry. Okay. So we were here. Okay. Can you see my screen now?
Yes, sir.
Okay. So CS value you can find out using this graph. So you are the only one in this session. I don't know. Others no.
No, they're also there.
Okay. Yeah, there. Okay.
I thought my screen got stuck or something.
Okay.
That's why I was.
No, I didn't share. I think
I
so.
couldn't
That's the
tell
reason.
earlier.
Okay. So CS again. I need to
Yeah.
mention in here. Get the reasonable value. Okay. So don't get the value close to the 0.6. It should be reached to close to the 0.7. Okay. And CS value. Then you need to find out the ultimate tensile strength at the Chendergos 6 cycle. Okay, infinite particle item. So then this is the equation. Sn prime, it is equal 0.5 times Su. This is ideal case. So it should be substitute here. So then you can get the endurance limit for this case. So this is the value. And so I hope you know how to get these equations. Can I give the pins?
So for the maximum stress,
Yes.
the nominal stress, that
Okay.
changes with the shape of the structure, right?
Yes, of course, you are right. But in here, you don't worry about that because they gave for us for the circular shape equation. So bending moment, you should know y is normally d divided by 2 in here because uh, it will be like this shape, no? In here, they provide this cross-sectional diameter. So normally bending moment, you will get this distance. This is y. Okay. So this is d divided by 2. I is normally 5 d to the power 4 divided by 64 for the circular shape cross section, isn't it? So later on, you don't want to keep it. I will show you how to get this equation very easily. But in here, you can't get that one because when we develop these theories furthermore, this equation will be shown in the graph. So you can get from that equation, get that equation from that graph. Okay. So, but it also depends on you. You need to select the proper graph. Then that graph has that equation. But in here, you should know the theory. So this is the equation between relationship between bending moment and stress. So you can put the y this direction, this side, and m times d divided by 2 moment of inertia, second moment of inertia, this one. So then we simplify that one. So d to the power 4 will be cut off to d. It will be simplified to d to the power 3, and 64 will be cut off by 2. Then it will be 32. It will become to upside. Then yeah, this will be simplification. Is it clear?
Yes.
Yes, sir.
Okay. So this is the equation for the circular cross-sectional elements. Okay. So maximum shear stress, this is nominal stress, so you can find out using substitute, using bending moment and other dimensions. So at the loading point, bending moment you can get from this equation. Okay, so bending moment. Yeah, I need to go. So bending moment, you need to find out the values in here. Say, 2 divided by 5 means it is 0.4f. Okay, this is 0.6f. So that's why 0.4f times distance. It is 150. Okay, in here, this one, this value. If you get the 0.6 f, 0.6 f times 100, it is also 150. Okay, so at the maximum bending moment point values you need to get. You need substitute here and dimension you substitute, and you will get the equation with the f. So then that value should be equal to this value. if it is 10 to the power 6 cycle. Okay, so if it is equal to this value, so you can find out the F. This is the value. So are we clear about that? Any questions? I can't hear you.
So what is that Fn? What does it represent?
Means that normally at the endurance limit we will put Sn. No? That's why it is Fn. Okay.
Yes.
This notation mentioned at the endurance limit. That means it's reached the endurance limit. Okay.
Okay.
Okay. So then that third question, C part, at the C part they ask the another questions, but you need to know the equation of the curve. Okay, because I will show you again. In here, they ask 5 times 10 to the 4 cycles fatigue life. But we know for this for the steel endurance limit 10 to the power 6. That means that particular materials below the 10 to the power 6. So when we draw the SN curve, it will be something like this. So 10 to the power 6 cycle we can find, but if it is 5 times 10 to the power 4, it will be somewhere here. So you need to know the equation of this curve. For that, okay, second point we know, first point we should know, then we can derive the equation. So that's why in here, find out 10 to the power 3 cycle strength. So it's basically not change with the surface factor, dimension factor, anything. So it's simply 0.9 SU. You can get the 10 to the power 3 cycle strength. Then same way you can find out the load value at the 10 to the power 3 cycle, because this is stress or strength. So use that equation, same. So then same equation, okay? These two don't change. So you don't want to do this step again. You can use this one, and it should be equal to this value, and you will get the 10 to the power 3 cycle load value. It is relevant to this strength, okay? So then you will get the load.
This equation, they've used 0.4 times F, and the early one for the nominal stress, they use 0.5. So is the largest stress for the...
Can you repeat again?
I said in the early equation, the step
In
above,
here.
they used...
In here.
Yeah, I thought my one says they use 0.5, mine must be wrong. So both the M is the same, right? Like the nominal stress doesn't change in value? For
This is not change. This is same value. Because this is this value not change, but F will be changed. Okay. So because bending moment not change, so we are going to find out that the loading point 10 to the power 3 cycle is strength. So function is same, but if it is stress change, that load value also will be changed. Okay.
Yeah. Okay.
Because bending moment equation is not change, and other things not change. Dimensions also constant. Only change the strength. Okay. So that's why load will be changed. So 10 to the power 3 cycle allowable load is much higher rather than the here. You can see, because it will not damage too much. That's the meaning of that. With the number of cycle increasing, what happened? Sample will be damaged. That's why the allowable load will be reduced. You can see at the 10 to the power 3, it can allow 43, around 44 kilonewton. But at the 10 to the power 6 cycle, it is allowed only around 15. Are we clear the answer?
Yes, sir.
Okay. So then you know the equation of S a into the power b. Okay, so same thing. So it is explaining here as well. So same thing. Okay, so you can draw the Fn curve as well. So if you have a Sn curve, that is mean strength versus number of cycle. So strength also we can take from the load, isn't it? So load versus number of cycles, that means Fn curve also will get the same equation, same type of equation. Okay, so that's why they get the Fn curve here. So then we know the loads. We are not normally deal with the strength or stresses, because stresses will change with the area. Okay, cross-sectional area change with the time. So that's why we are not going to deal with the stresses. So later on you will understand what is the meaning of that. Okay, so keep it mind this one. I will discuss this thing later. Okay, so why we select the load instead stress to analyze. So stress we can't, because so I need to explain more theory to explain that one. That's why I'm stick here with that statement only. Okay, keep it mind. So when you analyze, normally we are not deal with the stresses, we will deal with the force. Okay, so 10 to the power 3 cycle load value you know, and number of cycle you know, it is 10 to the power 3. So in here they substitute 10 to the power 3 here. Okay, for the end they didn't use the log expansion in here, just use simple equations and substitute. And this is 10 to the power 6 cycle F value. This is 10 to the power 6. You can see for the n they substitute here 10 to the power 6. Okay, and then that two equation should be equal to these two values, isn't it? This value and this value, 10 to the power 3 load and 10 to the power 6 load. This is that because if you draw the Fn curve, that initial point and this point, if it is on this line, it should, that equation should be satisfied these 2 points. Okay, so then you can find out a and b. So for that equation 1 and 2, you can divide 1 by 2 or 2 by 1 and get the b value and substitute to b value 1 equations and get the a. It is very simple calculations. Okay, so this is a and b. You can see, if you want, you use log. Okay, don't worry. Then you have equation. If you know the a and b, you have equation. What you need to do? Substitute here number of cycle, then you will get the F value. That's all. So hope you understand that third part as well. So any questions? So in these questions, we discussed 3 parts. So I hope you don't have any questions about that questions. So second questions. So I will briefly explain that one. Okay. So draw the shear force diagram. I will not going to read this question. Okay. And what is the maximum level load and what is the maximum level load for this number of cycles? So similar manner. So two loads are there now. So you have 2 weak points now. You need to find out which one is significant now. So using a bending moment, so bending moment diagram. In here they have mentions. Okay, so you can see they get the equations. Can you hear me? Because I got the message. My internet connection is unstable. Can you hear me?
Yes, sir.
Okay. Okay. So then these are the bending moment equilibrium. This is force equilibrium, and in here you can see that don't think too much about this kind of arrangement, because what they did, they will get the bending moment here to here, okay, and here to here and here to here. That's the explanation of this inequality. Okay, so they use the 0 to 100 This is bending moment, and 100 to 150 millimeter. This is bending moment. So equations they derive. It's up to you, and they simplify that one, and then draw the shear force and bending moment diagram. So you can see maximum bending moment at the second loading point, 0.6 F. Okay. And again they find out CL, CD, and CS. So I'm not going to go through these things. Okay, you know how to deal with that one. And then this equation 10 to the power 6 cycle strength. You can substitute the values and get the value. And bending moment, sorry, stress, maximum stress at the loading point. So for that you need to use this point stress. Okay, this one. So you can get the load value similar manner earlier we did. Okay, and 10 to the power 3 cycles. If you get the load value in here, so 10 to the power 3 cycle and equation, and find out the A and B and the value. Same thing. And in these questions, third questions, what they did, they have the data, real data point. They did 36 number of tests, and they find out the stresses with the number of cycle. So you can see some of they put the note 16 test and 17 is they didn't fail. That means it is reached to the endurance limit. Okay, so with this stress, with this amplitude stress, this kind of amplitude, so this is much higher. Okay, that's the meaning of that. So with this stress, it can be break, it failed. So if you consider the SN curve, it is somewhere here. That's the meaning of that. So stress is lower than this endurance limit. It didn't fail. So what you need to do, you need to find out the maximum value in the didn't fail testing. Okay, this one. So you can see the maximum value, it is around 417.15. So it didn't fail. That is the endurance limit. Okay. So you can draw the curves like this. Okay. So you can draw the curves, and you can see lower limit as well. So
Sir, shouldn't we take the lower limit to be conservative instead of taking the maximum limit?
we can, because can you repeat your question, because I got some wrong idea, I think, what you asked.
Because there are a set of specimens which did not fail, right? And there's a maximum and there's a minimum. Now, if we take the minimum, at the SN, if we take it as SN infinity, where the number of cycles equals infinity, right, for our graph,
yes,
wouldn't that be better? Because that would mean that every specimen there would reach infinity, and that would be the certainty.
So that's the meaning of lower boundary. So I just talk about the upper boundary. So you can see here, so that red color one explain the upper boundary, the green color one explain the lower boundary. So if you're going to minimum value from the didn't fail experiments, in among the didn't fail experiments, the minimum value explain the lower boundary, as you say.
Yeah, it's the lower boundary, but earlier we had the upper boundary and the lower boundary, and then we used the lower boundary.
Yeah, so we need to focus on the lower boundary then, of course.
Okay.
So then in here, you don't want to do this too much calculation, because her real data provide. So what you need to do, draw the curves. This is actually what they did in here, they normalize it. Okay, divide by SU, then normalize, get the curves, And then if you have some values, so in this question they were theirs, you need to find out the fatigue limit. So for the fatigue limit, they will consider the this value actually in here. Am I right? Yeah, 5.4. But don't worry, because the lower limit it doesn't. I mean, the so many testing data above that limit. That's why. But this is the lower boundary. Normally, when you are going to do the calculation, we will consider lower boundary. Obviously, yes, but there's so many data will be distributed around this red line, isn't it? So that's why they consider the fatigue lifetime somewhere here. Okay. So don't confuse too much about that. Can you see? Because they consider log n 5.4. That's how they find out the fatigue life. Okay. So they find out the fatigue life for this red color line, not for the green color. Tihan, are we okay?
I understand why they found it for the red line, because earlier they took it for the lower bound.
I got your sound up and down. I couldn't hear properly.
I said the earlier graph they took it for the lower bound.
Yeah, that's true. That's true. But in here, so many data point around the upper boundary. No, that's why they consider the upper boundary, because 2 or 3 data points available for the lower boundary. That's why. Don't think too much about that. Okay. So if you got this value, doesn't matter. You will get the marks, of course. I think. Okay.
Okay, sir.
Okay. So then they asked another 2 questions. Fatigue strength at the 1 times 10 to the 5 cycles. So convert to the log value, and it is around 5. So then from the red color one, you can get the strength, red color curve. If you use green color one, no worries. Okay. So if you use green color one, still it is endurance limit, isn't it? Because if you get the green color, it is endurance. It is endurance limit reached below the 5. Okay. If you got the green color curve, say you will get the same answer in here. If you got some answer somewhere here. Okay. So this value get from the red color one. So this value also get from the. They provide the stress here. So if you got the stress, you can find out the number of cycles. Okay. So you will get the log value. So you will need to convert to the real value. Okay. If you move to the 4th questions, I think it's the last question. Is it? Yeah, there's 5 questions, but I will explain this one only. Okay. Is it okay? So in these questions, you need to find out the minimum diameter. Okay. So calculate the minimum diameter. So they didn't provide the diameter actually, but they provide the function of diameter with the load factor. Okay, you can size factor. With this load, you need to find out the minimum diameter. So same calculation, but when you focus that questions, you will get the CL, CD, CS. So same way, I'm not going to explain how to get the CD, CS, CL. Okay. But when you get the CD, you have to get this function. Okay. You need to consider that particular component in here. If it is equal or less than 8 millimeter, CD value 1, and if it is higher than or lower than 8 millimeter and lower than 250 millimeter, this is the equation. And so you need to deal with the 2 case now. In here you can see. So CL, CS is fine, but CD will change with the diameter. So still you don't know diameter. You need to find out diameter. So that's why we will deal with the two cases now. So integral stimulus has two equations now. So if it is below the 8 millimeter, you already have strength. If it is above 8 millimeter, you have equation. So maximum stress point is again still there is no any stress consideration. That's why only loading point is available. So you need to consider loading point and bending moment and other things substitute. Find out the maximum allowable force using this one. So this equation should be equal to this one if it is 8 millimeter. If D equals 8 millimeter or less than, this one should be equal to this, isn't it? So then you can find out the allowable force. So this is the value. So this value, if it, you can see that value, it is higher than, sorry, it is less than 20 kilonewton. Is it? What is the 20 kilonewton? The first question, yeah, in here. That is the applied load. So if it is less than, definitely 20 kilonewton cannot withstand with this diameter. Diameter should be higher than 8 millimeter because allowable maximum load is 300, around 400 Newton. But we are going to apply 200 kilonewton, that means 2000 Newton. 2000 Newton we can't apply with the diameter 8 millimeter because if it is, even though it is 8 millimeter, it can allow 400. So that's why. So the first case is eliminate now. So we need to deal with this one above 8 millimeter. So then it will be above 8 millimeter. So then use that equations, find out the diameter. So, okay, so same thing. If it is 20 kilonewton is higher than this one, 40 kilonewtons, we don't have to explain because 40 kilonewton definitely it is higher than. So diameter again above 8 millimeter. So then same thing, you can find out diameter using that equation. So any questions until that point? So you can deal with this question. Okay? I'm not going to go through that. So again, you need to find out the minimum diameter. So you can use it, but they provide different relationship between the diameter and other. So you need to select the proper equations, and according to that you can draw and do the calculation. So I hope you can do the exercise alone and get the idea. If you have any question, you can ask next time. It was 2 hours now. Yeah, are we okay with the tutorial 2 and lecture number 3?
Yeah, that's fine, sir. This is not.
I'm not.
Choose not.
Huh? Sorry.
No, when they introduce stress raises, it becomes a lot harder and all that.
Yeah, definitely. Stress raiser, when you interest, it is a bit harder, but you should get the correct idea about this part first. Then otherwise, you are in trouble with the stress raiser because if you don't know this part proper manner, you are in big trouble at the stress raiser when you introduce the stress raiser because you don't know why we are doing this one, no, why we are going to apply this one or something like that. So
Yeah, definitely.
another thing, I'm not only teaching to Tihan, okay, others not raise their sound. I don't know why. So no point to explain. Yeah. Any questions?
No, sir.
Okay. So everything is clear?
Yeah, sir. Up to now, yes.
Yes. Okay. So I will give the date and time for the lecture 4. So I will upload this one in the course web. I recorded this lecture. So I think it's saved in my computer. If it is not saved, I'm in trouble. But if it is saved, I will upload in the course web and I will send the course web access to Tihan, I think you can distribute between others. Okay. And
Sure.
if you want to refer this video, you can refer, no worries. So I think you already refer the iLectures. So this is for additional thing. So if you have time and if you want, you can refer that one as well. So I will inform next meeting when we are going to do, but I prefer if you are joining to this lecture as well, because otherwise I hope you are not doing this tutorial alone, no? You just go through the with the solutions, but keep in mind you need to do the answering yourself. Otherwise, you don't know what you need to do at the exam. Okay. In my experience, I'm telling that. Otherwise, okay. So now it's good night, no? Okay. Good night for everyone.
Good night, sir.
Good night,
Good
sir.
night, sir.
Thank you.